4.5 billion years ago, amid the relentless swirl of the solar nebula, a small region within the inner disk condensed into the third planet from the Sun. Here, silicate minerals and metallic iron accumulated into a growing protoplanet that would one day support oceans, continents, and life. But its birth was anything but tranquil. Collisions, melting, and catastrophic impacts marked its formation. The Moon itself would arise from one of these cataclysms, born of fire and debris before both worlds cooled into stability. The timeline of Earth's history comes from studying radioactive elements that decay very slowly over billions of years. By measuring uranium and lead in tiny zircon crystals, scientists find that the first solid materials in the solar system formed about 4.57 billion years ago, and Earth itself finished forming around 4.54 billion years ago. Another method, using hafnium and tungsten, shows that Earth's metal core separated from the rocky mantle within the first 30 to 100 million years after the solar system began. In short, Earth and the Moon took shape near the end of a violent period of planet building when giant collisions were still common. Within the early solar system, temperatures exceeded 1000 Kelvin. Volatile ices were absent, refractory materials dominated. The earliest solids, calcium, aluminium inclusions, and chondrules, aggregated into planetesimals thousands of kilometers across. These bodies collided, merged, and occasionally shattered, their evolution governed by gravity and chance. The growing Earth swept up smaller fragments while competing embryos, such as those that would become Venus and Mars, did the same. Computer simulations suggest that in the early solar system, between about zero point 0.5 and 1.5 times the distance from the Sun to Earth, hundreds of small worlds, each the size of the Moon or Mars, formed within a few million years. Over the next 50 to 100 million years, these bodies crashed into each other and merged, leaving behind the four rocky planets we know today: Mercury, Venus, Earth, and Mars. The way their orbits and spins balance out matches what we see today, giving scientists confidence that these models of early planetary collisions are accurate. As accretion proceeded, gravitational energy and radioactive decay heated the young planet. Iron melted and sank toward the center, forming the core, while lighter silicates rose to create the mantle. The process released latent heat, raising interior temperatures to several thousand Kelvin and keeping much of the surface molten. A global magma ocean enveloped the early Earth. When Earth's metal core formed, it released an enormous amount of energy, enough heat to keep much of the planet molten for millions of years. As the molten iron sank to form the core, it pulled down iron-loving elements such as nickel, cobalt, gold, and platinum, leaving the rocky mantle poorer in these metals. This separation also changed the mix of tungsten isotopes in the mantle. By measuring these isotopes, scientists can tell that about 90% of Earth's core formed within the first 30 million years after the solar system began. The Earth's proto-atmosphere at this stage consisted largely of hydrogen and helium captured from the nebula. Because of the Sun's strong ultraviolet radiation and planet's weak gravity, this primordial envelope was quickly lost to space, leaving behind a bare, molten world surrounded by silicate vapor. The young solar system remained chaotic. Jupiter and Saturn migrated through the disk, altering the orbits of countless planetesimals. Collisions rained debris onto the inner planets, adding mass and volatile elements. Asteroids and comets delivered water and carbon-bearing molecules to Earth's surface, though most of that surface was still molten. According to computer models like the NEAS model, after the solar system's gas and dust cleared away, about 3 to 10 million years after it formed, the pull of gravity between Jupiter and Saturn upset the balance of smaller icy and rocky bodies in the outer solar system. This caused a wave of impacts about 4.1 to 3 billion years ago, known as the Late Heavy Bombardment. Evidence from craters on the Moon shows that many impacts happened during this time. The bombardment likely melted and destroyed much of Earth's early surface, but it may also have brought in water and organic molecules from distant asteroids, setting the stage for life to begin later. The chemical makeup of Earth's water, especially the ratio of deuterium, or heavy hydrogen, to normal hydrogen, is almost the same as that found in certain carbon-rich asteroids. This means that most of Earth's water probably came from asteroids, not comets. This idea was confirmed by the Rosetta spacecraft, which measured much higher deuterium levels in the water from comet 67P, showing that comet water is quite different from Earth's. One of the last giant impacts in Earth's history was the most dramatic of all. A planet around the size of Mars called Theia crashed into the young Earth at a glancing angle and tremendous speed, around 10 kilometers per second. The collision released an enormous amount of energy, melting both worlds and throwing huge amounts of rock and vapor into space. That debris eventually came together to form the Moon. The giant impact hypothesis explains multiple lines of evidence: the Moon's large relative size, its depletion in volatile elements, and its isotopic similarity to Earth. High-precision analysis shows that terrestrial and lunar rocks share nearly identical oxygen, titanium, and tungsten isotope ratios, far closer than any other solar system bodies, indicating a common origin. Computer simulations reproduce these features when the impact mixes Theia and Earth's mantles thoroughly before the debris condenses. The angular momentum of the present Earth-Moon system corresponds to a total rotational period of roughly 5 hours immediately after impact. Tidal interactions have since transferred angular momentum outwards, slowing Earth's rotation to 24 hours and pushing the Moon to its current 384,000 kilometer orbit. Ancient tidal rhythmites, sedimentary layers recording daily cycle, confirm that 2.5 billion years ago the Moon was only 60% of its current distance and days lasted 18 hours. Alternative models have been explored. Multiple smaller impacts capture scenarios of fission from a rapidly spinning Earth. None match the isotopic and dynamical data as successfully as the Theia collision. Recent refinements suggest that Theia's composition was roughly identical to Earth's, explaining the isotopic similarity, or that the impact produced a synthesis, a transient donut-shaped mass of vaporized rock from which both Earth and the Moon condensed. The Theia collision left Earth incandescent. For months or years, the surface remained an ocean of magma thousands of kilometers deep. while a dense atmosphere of silicate vapor, steam, and carbon dioxide enveloped the planet. The newly formed moon, glowing red hot, orbited just 20,000 to 30,000 kilometers away, so close that it loomed 20 times larger in the sky than it does today. Tides between the two bodies were immense, and the Earth's rotation period may have been as short as 5 hours. Computer models suggest that after Earth's violent beginnings, the planet was covered by a global ocean of molten rock hotter than 2,500 degrees Celsius. It cooled very slowly, taking a few million years to solidify. Early on, the atmosphere was filled with gases from vaporized rock, but as the planet cooled, these minerals condensed and fell back to the surface. This left behind lighter gases such as water vapor, carbon dioxide, sulfur dioxide, and nitrogen, which escaped from the interior through volcanic eruptions. During this time, the atmosphere may have been hundreds to thousands times thicker than it is today. When the moon first formed, it orbited very close to Earth, only about 3 times Earth's diameter away. Its strong pull created powerful tides inside Earth's still soft mantle, which helped the planet cool faster. Over the first 100 million years, these tidal forces released almost as much energy as the moon forming impact itself. This close relationship between Earth and the moon also helped steady Earth's tilt, giving the planet a stable climate over long periods of time. As heat escaped into space, crystals began to form in the upper layers of the magma ocean, creating a primitive crust of anorthosite and basaltic composition. Iron and nickel continued to sink inward, completing the segregation of the metallic core and generating the magnetic dynamo that would one day shield the atmosphere from the solar wind. The remaining mantle convected vigorously, cycling material between surface and interior. Studies of earthquakes and Earth's chemistry show that the core makes up about 1/3 of the planet's mass and extends to a depth of about 7,000 kilometers. The outer core is still liquid, made mostly of iron and nickel mixed with small amounts of lighter elements like sulfur, oxygen, and silicon. Deeper down, the inner core has solidified, forming sometime between 1 and 2 billion years ago. As it froze, it released heat that keeps Earth's magnetic field running today. Evidence from tiny magnetic crystals in ancient rocks from Western Australia suggests that Earth may have had a magnetic field as early as 4.2 billion years ago. Earth's first crust was probably short-lived, constantly destroyed and remade by powerful impacts from space. But chemical clues inside ancient zircon crystals show that liquid water was already present by about 4.38 billion years ago. This means parts of Earth's surface had cooled and solidified enough to hold oceans or lakes within only 150 million years after the moon formed. The moon too bore the scars of its fiery origin. The debris disk that spawned it produced a body largely molten. As it cooled, lighter anorthite crystals floated to the surface, forming the bright lunar highlands, while denser materials, olivine, pyroxene, sank to create the mantle. Meteorite bombardment soon pocked its face with craters, recording the violence of the solar system's youth. Moon rocks brought back by the Apollo missions include Pharoan anorthosites, lightly coloured crustal rocks dated to about 4.36 billion years ago, showing when the Moon's global magma ocean finally solidified. Later volcanic rocks, called mere basalts, reveal that lunar eruptions continued on and off until about 1.2 billion years ago, long after Earth had cooled and stabilized. The chemical makeup of the Moon and Earth, including oxygen, titanium, and chromium isotopes, is nearly identical, proving that they came from the same material. Today, laser measurements show that the Moon is slowly moving away from Earth at about 3.8 centimeters per year as their gravitational tides continue to interact. With the magma ocean crystallized and impact flux declining, volatile gases began to condense. Water vapor rained out, filling the basins and lowlands to form the first oceans. Carbon dioxide and nitrogen remained in the air, creating a dense greenhouse warm atmosphere. The young sun's ultraviolet light drove photochemical reactions, producing hazes and potentially organic molecules that settled into the area. Volcanoes and heat inside the young Earth released huge amounts of water vapor and carbon dioxide, enough water to fill oceans several kilometers deep. Scientists think that most of Earth's water came from this internal source, with the rest added by impacts from water-rich asteroids. Tiny ancient crystals showed signs that liquid water existed about 4.3 billion years ago at mild temperatures around 30 to 40 degrees Celsius. This suggests that a thick atmosphere of carbon dioxide and nitrogen kept the planet warm even though the sun was dimmer than it is today. The earliest atmosphere lacked free oxygen. Instead, methane and ammonia produced a reducing environment. Lightning and ultraviolet radiation acting on these gases could synthesize amino acids and simple organics, as demonstrated in Miller-Urey type experiments. The balance of carbon between atmosphere and ocean established early chemical cycles that would later feed the emergence of life. The Moon's gravitational influence quickly became a regulating force. Its tidal pull slowed Earth's rotation, lengthening the day and dampening variations in axial tilt. Without it, Earth's obliquity might have wandered chaotically, leading to extreme climate swings. The stable tilt of 23.5 degrees, oscillating only a few degrees over tens of thousands of years, produced regular seasons that would shape future biological rhythms. Dynamical simulations comparing Earth with a hypothetical moonless planet show obliquity variations up to 60 degrees over million-year timescales. The presence of a large moon increases the planet's moment of inertia and shifts resonance frequencies away from those driven by Jupiter and Saturn. This stabilizing effect likely persisted throughout Earth's history, influencing not only climate but also tidal patterns essential to early coastal ecosystems. Meteorites preserve snapshots of the solar system's early chemistry. Anstatite chondrites share isotopic affinities with Earth in oxygen, silicon, and titanium, implying they originated from the same inner solar region. Their highly reduced mineralogy supports models in which Earth accreted from material formed under low oxygen conditions inside 1 AU. Iron meteorites, remnants of differentiated planetesimals, record metal silicate separation ages consistent with Earth's core formation timeline. Collectively, these extraterrestrial samples anchor the chronology of planetary growth. No rocks older than 4 billion years still exist on Earth, but tiny zircon crystals found in Western Australia preserve chemical clues from as far back as 4.38 billion years ago. Their makeup shows they once formed in the presence of liquid water and came from recycled crustal material. These microscopic minerals prove that continental crust and stable oceans already existed very early in Earth's history, less than 200 million years after the planet was first formed. The making of Earth was a saga of accretion, collision, and transformation. Out of a disk of dust came a molten planet from a catastrophic impact, a stabilizing moon. The surface cooled, oceans formed, and the first atmosphere condensed beneath a young, brilliant sun. By 4.3 billion years ago, Earth had become a world of rock, sea, and sky, its violent infancy giving way to the long rhythms of geology and time. In the next episode, the focus will turn to Hadean Earth itself, its molten landscapes, early crust, and the gradual emergence of conditions that would one day permit life to begin.